Oh, okay. I'm doing not that bad. It's okay. We're gonna get there. So I present to you the Bayesian total evidence dating model. So remember we talked that the models have components, right? So we can build very complex models using modules, right? So think of this as a modular structure. So we have ways in which we model morphology, ways in which we, and these components, it's going to explain how traits change, right? So the Bayesian total evidence dating has three main components. I want to know how traits change. I want to know or estimate at what rate they change. And I want to place that into a time tree. So a tree that is correlated to time. I just skipped through this, sorry. So we have morphology, we have rates, and we have the time tree. And if you think back, so we're basically separating these three parameters. So V is how my characters change, right? The rate comes from the clocks, the clock models, and the time comes from the tree model, which is informed by the fossils. Approach this model, we're separating rate from time. So what I'm going to do now in the next slides is to go over the three main components of the model. When you're specifying your model in RevBayes, you will have to specify these three components. And we're going to talk about some of the questions you have to ask yourself before specifying each of the models. So then you can go through the code and think about that, okay? So let's start about the first part of the model, the first component. So how the traits change. And we're gonna have, usually what we do is we compartmentalize these. So we're gonna have a model for morphological traits and a model for molecular traits. Let's start with molecular traits. So this, and for that, we have a bunch of information. We have a bunch of models. I'm sure you all have heard at least about GTR plus gamma, right? What I want you to keep in mind is that we basically need two parameters in this model. This is a pretty standard model. I feel like you should feel safe about using this model in general. So we need a rate matrix and we need a gamma distribution. So a rate matrix basically describes how we change from one nucleotide to the other nucleotide, right? And this GTR is symmetrical, so we assume that the rate of change in one direction is the same as in the other direction, right? So we have basically here these 6 different parameters. And we have a gamma distribution. So you're gonna see that we usually use gammas to accommodate for variation, right? All the positions in an alignment change at the same rate. Why? Why wouldn't you expect that all the nucleotides in an alignment have the same rate Q matrix?
Because we don't know whether we have been selected.
That would be one, yes, selection.
Because the codons, not every position has an effect. So it may not be deleterious. It may not actually.
Yeah, so we don't know if they're being selected, but there's one that is like super evident in coding regions. Oh yeah. I can't hear you, but oh.
Yes. Are you talking to me?
Yeah, can you repeat what you were saying?
I was saying that there's positional significance and effect based upon the position of a nucleotide. In that some things, some mutations don't really have an effect. They're silent mutations. That's what I was talking about.
Yeah, excellent. Ooh. And that is basically with the position of the nucleotides, right? We expect more changes in the third position because we have redundancy in the code. And even if the third position changes, it may not have an effect on the amino acid. So we expect third position to change faster. For that variation, we use a gamma distribution, which basically what it does is it says that different positions may have different rates. So we use the same Q matrix, but we put them in different bins. So in this case, I would be using 4 bins, and I would multiply by a value. So this is changing faster, so I'm going to multiply it by 3. This is changing slower, so I'm going to multiply it by 0.5. And I have like bins, and that's how I allow my nucleotides within the same alignment to have different rates. Okay. So that's pretty standard. And because there's so many tutorials about molecular evolution, that's as far as we're going to go. Morphological evolution, we need the same. We need a model that describes how morphology changes. Evolution are harder. Can you guys tell me some ideas of why modeling morphology is harder?
Incomplete fossil record for one.
There's not an easily generalizable model for morphology, right? Different traits change for different reasons. Also, we have different number of characters, right? In DNA, we have ACGT, and that's all the states you may have, right? In morphology, for one state, I can have with flower, without flower. For other character, I can have, I don't know, pistil, like together or like separated, and it's not the same. They're not comparable. So I cannot generalize, okay? This is where the knowledge of biologists is really and the models we have are actually quite simple. There's a bunch of people working on this. I think at some point we're gonna get better, but the simplest model would be a model in which I have a binary trait. So with flowers, without flowers, or vice versa. And then I will assign rates. So what is the rate of going from not flower to having flower and vice versa, right? This is what we call the MK model, right? We could extend this for 3 characters, right? So it could be green, yellow, pink, whatever. Yes.
So by looking into the evidence, how many times that particular morphology has changed, we'll be able to estimate how we see the changes in that particular morphology, and from that morphology. And hence it is a naive.
Yeah, that's what we do in many of the so-called comparative methods, where we're trying to estimate the rates of change through time, right? We could, of course, apply that if we had like prior beliefs on how a parameter, how common a trait is. We could implement that in our model when we're making inferences. So that's part of like why it is important for you to be able to modify your model, and why it is good to use programs like RevBayes that allow you to code what you think is happening. Yes.
How about visions in morphological characters? We have different, like, several morphological characters that you can evolve one way, and some that can you do partitions in the way that you do also for a molecular context?
Yes, you can do partitions, right? But again, is to partition first by the number of character states. So binary characters in one partition, with 3 states in another, with 4 states in another. But the reality is that every morphological character is different. And sometimes just like making groups, it's hard to even start thinking about that, right? But that's why biology is important, because maybe your solanase is so good that you could say like, oh, these traits should actually, I think they behave the same, so let's make them a partition, right? So yeah. Okay, so we were on the MK. So the MK has the same rates from 0 to 1 and 1 to 0. But of course, what we were just discussing, that's not always the case, right? We know that some traits, probable, like some transitions may be more important in one direction or in another, on us to how to make these models more complicated. So for example, we would have an MK plus gamma that would allow different traits to change at different rates, but symmetrically, right? MK plus gamma. If we want to account for the different rates from one state to the other, then we have a model that is called F81, right? So we can make this as complicated as we want. And as you see, we can incorporate different biological processes. So the variation among traits, the fact that they may not be symmetrical. So you can make your model as complex as you want. Although you have to consider that then you may not have enough data to do the kind of partitions you want. So it's always this like juggling between having enough data and perfect, right? It's a model. So we can still accommodate some variation without having to like come to the point where we have like one model per character.
Morphological sometimes they are big and dogs multiple phenotypes on them. They because of I don't know much about it, but when one changes, the others also improve the years, show up alongside with and or behave. Can we account for the, or do we always consider changes in morphological characteristics?
Say again that last part, changes in morphology.
Do we consider them always to be different, or they be like cleared of the effect of like one change that happens?
Specify that on your model too, so you could make your characters to be correlated, right? So you could specify a model of correlation among certain partitions, for example, right? That for me, like now you were talking about, that's pretty straightforward when you have continuous traits, right? You could make continuous traits correlated. And I guess the answer is yes, you can go as complicated as you want and as your computational time allows and how much data you have, right? So one of the, I wouldn't want to call it a drawback of this type of approach, Bayesian total evidence dating, but it's true that you need to have some morphological information and you need to have some modeling background and know how to code it. So it's a lot to handle for one person. So you may have like someone that can implement the model, but someone that knows very well the group, right? And the idea with this workshop is to get you guys started into like feeling comfortable to start approaching this in RevBayes and start looking at the tutorials, because there's a bunch of tutorials, but I know by experience that it's really hard to sometimes just jump in by yourself without having any background. No one is going to come out an expert of RevBayes, after this workshop, but the idea is that you may know, like, I want you to understand what we're doing in RevBayes when we're like putting all this code together, and how you can specify your model in a way that is good for your data, because the model has to be good for the data, right? Yes.
Now that we come like good evidence and like case but they're like, why not change like say like, oh, I don't like them.
Because we usually, I mean, a priori, you may not know, it would be like group specific, but I think you're going into something that I want to touch at the end, which is that even if we don't know at the beginning whether changes are symmetrical or not, what I could do is I could run my analysis with a model that specifies symmetrical rates, and then a model that allows rates to be asymmetrical. And then I could compare those two models. And I could see maybe the one that is symmetrical is better. So that applies better for my data, right? Like that model has a higher, it's better when we compare them. So I'm gonna go for that model. So we're getting into model comparison. And that's also good to say, because then we don't need to know everything a priori. We can try different options and see which one is better and fits better our data. So yeah, we can keep making this more complicated, but again, everything is a function of how much time I have, how much data I have, how complex do I want to make this. Let's move quickly to the clock models. So we finished with the molecular, well, the evolution models, so trait evolution, how traits change. Now I want to describe at what pace they change. And we talked before about the global model, so the one that says that there's one rate across the phylogeny. But the reality is that we don't expect that to be true. So mainly we use relaxed clocks. So a relaxed clock allows different branches to have different rates. How do we do that? We usually have a prior on how rates are can be distributed. So here an example where it is like a curve, but it could be flat. And basically I will draw values from this distribution and allow each branch to pick its own rate, the one that fits better to that branch, right? So all these things require you to specify, again, priors, and you can use priors like this. If you have more information, you can use other type of priors. Something I'm gonna say, just because if not, my mentors will be mad about this, is that it's interesting because often we think that a uniform prior is an uninformative prior, but that's not the case, right? So sometimes a uniform prior may be forcing things that we don't know, right? So it's always good practice to run your analysis without data, just to see that your priors actually look tutorials on how to do that, how to run your data without, your model without data. Okay, the relaxed clock is pretty straightforward in terms of how it is specified, but something that is interesting, because we're working with two different sources of information, we're working with morphological and molecular data, is that we can link or not the clocks. So we may think that the branches that change molecules faster may also change morphology faster. So in that case, I would like to have a clock that is linked, right? But I could also think that maybe that's not the case. Maybe morphology doesn't necessarily change at the same rate as molecules. And then I may want to try an unlinked clock, right? So again, we're coming to the fact that and sometimes we don't know, and then we have to compare models, right? I could compare a link model and an unlinked model and see which one performs better. And finally, we get to the time tree. So this part of the model, it's gonna describe how the lineages occur in time. So in absolute time, right? And the most used time tree model is the fossilized birth death. So let's just go a little bit in depth about this model. So this tree model comes from a process that has the same name, right? So why do we like this model? Oh, well, first, it was described by Heath and collaborators. It has parameters that are important for us as biologists and that have some sort of interpretation. So the parameters that it has is a birth rate or so-called speciation rate. So how lineages split through time. Then we have an extinction rate or death rate. So at what rate a lineage goes extinct. We have a fossilization rate. So at what rate do I have a fossil, right? And something that I just want to quickly call your attention about this fossilization rate is that maybe the name is not the best, because this rate is not only how often a fossil is produced, it's how often a fossil is produced, is found, is described, and is incorporated in an analysis. So there are a bunch of processes in the future to see work kind of changing this parameter or parameterizing it better.
That would be the fossilization rate plus the fossil recovery rate.
Yeah. Yeah, so one of the instructors of the other workshop that we thought of a little bit ago says that this should be called the fossil recovery rate. That's what Ben said. But yeah, so the message is that there are a bunch of processes that come into this parameter, just for you to keep in mind. And then we have another parameter that is the sampling fraction. The sampling fraction is how many of the extant lineages am I sampling, right? So I don't know, I work with a group that has 800 species and I sampled 8, right? So that's how I would get my sampling fraction. Okay. Comes from a fossilized birth death process. So let's use this process to simulate a tree. So we start at some point in time. So maybe you can see there that little gray dot. We start there. We simulate a waiting time. So we say we're going to wait a certain amount of time until something happens. And that something happens to be first a speciation event, right? So we could have different things. We could have speciation, extinction, fossilization. But the first thing that happened here is a speciation, right? Then we start with one of the branches, one of the lineages on top. So I continue my process. And then something else, that's my waiting time. Something happens after my waiting time, which in this case is a fossilization event, right? So I can leave a fossil. And I keep going. And then notice something interesting here is that I got a fossilization, but my lineage keeps allowing me to infer a fossil as a direct ancestor, which is pretty cool. So I keep going on my process, and then eventually I have an extinction event. Then I move to the next branch, and I keep doing the same until for each lineage, either I get extinct or I get to the present. Okay. And then, of course, in the present, we may have a sampling event. So some of these terminals I may not sample. And of course, I can take out all the lineages that didn't leave any fossils, all the extent. And this is probably like my process that I'm observing on my data. right? Depending on what I sample, what left fossils, and yeah, all that. So this is like a pretty, to me, like a pretty good way to parameterize, like a pretty descriptive model that has some biological model for the tree, okay? So we went through the 3 components. We use these 3 components in our Bayesian total evidence dating. And the cool thing is that they inform each other, right? So the tree is informed by the morphological data as to branch lengths. The tree is also informed by the clocks as to how fast the changes occur. And the time tree also, I should have put little arrows here, but the time tree is informed by the data of the fossils, and everything is estimated together, right? So we're co-estimating everything. So we're letting the different components of the model to interact and inform each other. So I think this is really cool. Yes, we have a question. Oh, wait 1 second. Yeah, so if your models are conflicting, you would start like having problems of converging, right? So there was a question about what happens when different components of the model conflict. And I guess the answer is that you would have a hard time getting convergence, achieving convergence. What is a good, just practical advice in general is that I like to try different parts of my model independently before running a full model, right? So I would first run an analysis only with my molecular data. The one that has the most data is having issues, then putting the other pieces together will be harder. So first try only with your molecular data. If that makes sense, you're good to go. Then maybe try the morphological data and good to go. And a lot of this is also, sometimes there are fossils that won't have enough information, and maybe you cannot make up information, right? You cannot make up data. So sometimes you just have to see what works. And if you don't have enough data to put a fossil, to place a fossil, it may be worth to just not use it, right? Okay. So this was like my speech about the model. There are many things that, because of time, we didn't really get to talk about. We talk a little bit about model comparison. So basically having 2 competing Bayes factors. There are tutorials online, so basically you can compare which one of the models is better. But something that is not as commonly talked about is the model adequacy, right? So I may have 2 models, right? I can compare them and I can say, oh, model A is better than model B. And then I can be happy. But maybe I shouldn't, because what if they are both really bad at giving me the kind of data I have? So that's what we call model adequacy, right? So I want a model, the best performing model, but I want that best performing model is able to generate data like mine, right? So this basically, what this does is that it runs my model with my parameters and gives me data, and I can compare the data with my data and see how similar they are. So see if the model I'm using with the parameters I have found. Does that make sense? So yeah, once you get into being able to run these models, it's worth to try this, right? I guess my point is, making inference is not enough. We have to make model comparison, make sure the model we use is adequate and is the best one that we can use. Okay. Questions?